Bismillahirrahmanirrahim. Welcome students to the online lecture of Digital Logic Design. In the today's lecture, we will be discussing the counters. In the previous lecture, we discussed the memory registers, and in the current lecture, we will be discussing the counters. We have initially discussed a little bit about the counters. Counters are actually a special type of registers, but their output follow a prescribed sequence of state. Say if they follow a certain pattern, the outputs of the register follow a certain pattern. We called it a counter. A sequence they could be of any kind. It could follow a certain binary pattern, or it could follow a certain other pattern. Say if a sequence is following a certain kind of a binary values, it is incrementing by a binary values, then we can say that it is a binary counter. If we have to represent as n-bit binary counter, then that should consist of n flip-flops. And for n-bit binary counter, we could have values from 0 to 2n minus 1. Say if we are dealing with a 3-bit counter, but 3-bit binary counter, then that 3-bit binary counter could represent values from 0 to 7. The counters are generally available in two different categories. First is the ripple counters, and the second one is the synchronous counter. The ripple counters are, you can say, are example of an asynchronous binary counters. In a ripple counter, we have a circuit of flip-flops in which the sum of the flip-flops are not controlled by the main clock signal, but they are controlled from the outputs of the other flip-flops. So it means that the main clock is not affecting the all the flip-flops that are involved in the system. Some of the flip-flops may be governed by the main clock signal, while the rest would be controlled by the outputs of the other flip-flops. But in a synchronous counter, all the flip-flops that are involved in the circuits receive the common clock. First, we will be discussing the ripple counters. Here we are discussing example of a binary ripple counter. A binary ripple counter is a connection of different flip-flops. Each of the flip-flops that is involved in this circuit is a complementing flip-flop, or you can say the toggle flip-flop as we used to call it, or T flip-flop. We could also design this T flip-flop using the JK flip-flop, because if you remember the table of the JK flip-flop, if we just combine the two inputs J and K together, then it's equivalent to complementing the current state of the flip-flop. So we could also represent it in a form of a JK flip-flop. So what we have done here is that we have connected 4 different flip-flops, because we are representing here a 4-bit binary ripple counter. In this one, the first flip-flop is directly connected to the count signal or the main clock signal, and you can see that all the flip-flops have a buffer at the clock signal. So it is basically representing that they are operating on the negative clock edge of cycle. So all these are operating on the negative clock cycle, while their outputs are connected in a way that the output of the first flip-flop A0 is connected to the clock of the second flip-flop, and the output of the second flip-flop, which is represented as A1, is connected to the input of the next flip-flop, which is the clock signals, and the A2 output is connected to the clock signal of the A3 flip-flop. And all the inputs, the T inputs of the system, are connected to logic level 1. So they are operated in a way that the main pulse or the clock signal is only applied to the first flip-flop, while the rest of the flip-flops are connected in a way that one output is connected to the clock signal of the other flip-flop. So there is also a common reset pin available to all these flip-flops. If we set it to 0, then all the flip-flops would go back to their reset state. So they would have a value of 0, 0. And now if we want to represent this system in a form of a timing diagram, we generally represent it in a form of this way. This diagram is very important in terms of understanding the whole procedure of this binary ripple counter. Generally, you find this kind of diagram in the data sheets of different ICs. So it is very important to clearly understand that what does it mean. Suppose we have a count signal that is actually representing the clock signal or the main clock signal of the a circuit. Because all these are operating on the negative clock edge, that's why we are representing each negative edge by the arrow. So all the negative edge that are involved in this pulse train are represented by this arrow. Now after the first cycle, what happens that because the decision takes on the first or negative cycle, and initially we assume that all the values of A0, A1, A2 and A3 are equal to 0 or in the reset state. So when the first clock edge arrives, negative clock edge arrives, what happens is that because all the inputs are connected to the T, which is equal to logic level 1, and when we have a T value equal to 1 against a T flip-flop, then the output of the flip-flop is complemented. Say if we have A not equal to 1, then that would go to 0. If it is 0, then it would go to 1. So in the first place, because they were initially 0, so after the first cycle here, it would go to 1. So A naught would have a value of 1 here. But after the next negative edge, it would again go back to 0 because the T value is always equal to 1 here. So it would be complementing after every negative edge of the clock. Now if we assume the second flip-flop, now for the second flip-flop, the clock is not the count, but it is A1 because A naught is has become the a clock of the second flip-flop, which is represented as A1. Now it will all the decisions would again occur at the negative clock cycle of the clock. So we have again indicated all the negative edges through this arrows. Now what would happen that after the first clock negative clock edge cycle, because the value of t is equal to 1, so we would get a complemented value. So because it was initially 0, so it would move to 1 and it would remain there till we have the next negative clock edge of the cycle. When the next negative clock edge of the cycle arrives, at this point what happens is that our system value is again complemented, so it would again move back towards 0. And after that, when the next negative clock cycle arrives, at this point it would again move to 1. So in this way it would also keep on complementing. Now for the next one, A2, the similar procedure happens because for the next flip-flop A2, the clock signal is actually the A1. So all the decisions that are made in the A2 are basically dependent upon the negative edge that is present in the signal A1. So we have to wait till the negative clock edge appears in the A1 signal, and when it appears, then our system will get the complementing output because initially value was 0. So when it receives a negative clock edge of the cycle, a decision would occur, and because t is equal to 1, so it would complement this value and it would move it to 1. So in this way A2 is formed. Similarly, in the same manner, A3 performs. For the A3, A2 becomes the clock signal, and it again on the negative clock edge of the cycle, it will form the decision that what would be the output of the value because its initial value was 0, so it would become a 1 here. If you can see there from the first cycle that initially all the values are 0 0. After that negative clock edge, only the A naught is equal to 1 while rest of them are 0. After the second negative edge, what happens is that the A naught again comes back to 0 while A naught becomes 1 and A2 and A3 are 0. So you can see that there is a binary pattern that is following here in the output. First we had zeros here, then we had value 1 here, then we have by decimal equivalent of 2, then decimal equivalent of 3, then decimal equivalent of 4. So in this way the counter will keep on increasing its value from 0 to 15, and after 15 what will happen, that system will again move back to the reset state or the initial state, which is that all the values would again come back to 0 0 0 0. So in this way a basic binary ripple counter works. This binary ripple counter could also be constructed using a D flip-flop too. Is the configuration with the D flip-flop is presented in this way. What happens is that in the D flip-flop case, the complemented output of the flip-flop is connected to the D input for each of the flip-flop. The rest of the procedures according to the clock remains the same. The system still behaves on the negative clock cycle of the pulse. And again you can see that there is also the same reset function also available here too. So this would perform the same functionality as this circuit. Only difference is that now we are using the D flip-flop to implement this circuit instead of the T flip-flop. And if you consider the table or the truth table of this binary sequence from the outputs A0 to A3, then you can see that whenever there is a negative clock edge, which is actually a transition from 1 to 0, you can see there is a transition in the next state or in the next flip-flop. Similarly, when always there is a transition in the second state from 1 to 0, there is a transition in the third flip-flop. And similarly, when there is a transition in the third flip-flop, there is a transition in the fourth flip-flop. So in this way, the whole process works, and whenever it achieves the highest value, which is the 15 in this case, then it would again reset to 0. We could also make some slight modifications in the binary ripple counter to make it a binary ripple down counter, because the previous counter was a kind of a up counter in which our value was incrementing. Now we want to design a counter in which the values are actually decrementing. We will be starting with the maximum value, say 15, and then with every clock cycle or with every transition, our system will move down to one value, say from 15 to 14, then 13, 12 in towards 0, and when it reaches 0, it would again reset to the maximum value, which is 15. The basic circuitry remains the same, just there is a slight difference here, because now the system is operated in a way that each of the flip-flop involved in this circuit is actually triggered by the positive clock edge, not the negative clock edge, but all the signals are all the flip-flops that are involved in this system are basically triggered by the positive clock edge cycle. So what we have done is that first we have represented the main clock signal of the system by representing the arrow at the positive clock cycle. So each of the arrow is actually representing the positive clock cycle. And what happens is that because the output of the first flip-flop becomes the input of the second one. So when the first a positive edge occurs, then what happens is that because the value of t is attached to logic level 1, so the main input would be complemented. So if we assume that all the values values A0 to A3 have initial value of 0, then what would happen is that after the first clock cycle, it would A0 become equal to 1. Similarly, because for the A1, now the input is A0, the clock signal is A0. So what would happen is that because of this, as soon as this would go to 1, then this would become A0 would become basically the clock signal for the next flip-flop. And when this would go to 1, again A1 would move towards 1 because it is also has the complementing property. And similarly, this A1 is actually now become the clock of the A2 flip-flop. And similarly, the A2 flip-flop output has become now the clock signal for the A3. So in this way, when they are all operated on a positive clock cycle of the edge, we could see that when the first one, if we get the value of A0 equal to 1, then that would provide a positive clock edge cycle, and that would be able to represent the next value as the complementing value. Similarly, same procedure would follow for the A2 and A3. And now if you could see the values here, all the values here are equal to 1, 1, which is actually representing the maximum value of 50. Now after the next positive edge of the cycle, what would happen is that for the first flip-flop, its value would get complemented. So we would have a 0 here, and for that 0, there would be no change in the output of the next one, because for the 0, the value remains the same in the T flip-flop. So we would have a 1 here, and also 1 here, and also the 1 here. So in this way, we would get the value of 14 here. So next would be equal to 13. So in this way, this down counter works. One important thing is you have to note is there that at the positive clock cycle of the edge, it is not possible that each of them act at the same time, because this signal has to wait till the positive transition occurs, and after that it moves to 1. So it is just a few say millisecond or microsecond in reality a little late to move towards 1, and then when it moves to 1, after that this would move to 1, and after that this would move to 1, and after that this would move to 1. So actually all of them have a slight time delay, because they have to wait till the previous signal goes to 1, and after that they will be performing their corresponding operation. Now we would be discussing the BCD ripple counter. As you know that in the BCD the count is from 0 to 9, and to represent the 0 to 9 in a binary form we need 4 bits. So we would be basically requiring 4 different flip-flops for this circuit, and we can combine them in a form of a or represent them in a form of a state diagram in this way. This is representing the states, that how the states would behave. They would be behaving in a kind of a binary manner till they reach the value of 9. So because after the 9 there is no representation in the BCD, so what should happen is that system should go to the reset state, and that reset state is that starting state, that when all the values are equal to the 0. So what we have done here is that we have implemented this equation, or this state diagram, according to the techniques that we have discussed in the design part of the sequential circuits, and from that we have used the JK flip-flops to represent this system. In this one, the JK flip-flops are connected in a different manner. Some of the inputs are connected to logic level 1, while other have involved some kind of a combinational circuits in them. The each output is representing the basically the weighted value of the BCD code, which is 1248. So basically 1248 are representing the weights of the each bit. Now for this system to perform accurately in a form of a ripple counter, that initial state should be equal to the 0 stage, and if the say Q1 changes state after say, every clock pulse, because it is directly connected to the main count pin or the clock pin. So basically Q1 would be changing after each clock pulse, while the Q2 would complement every time the Q1 goes from 1 to 0, because all of them are based on again the negative clock cycle. So that's why Q2 complements every time Q1 goes from 1 to 0, and as long as the Q8 is equal to 0. And when the Q8 becomes 1, the Q2 remains at 0, because you can see that its output is connected to the complemented form of the Q8 here. Similarly, for the Q4 complements every time when the Q2 goes from 1 to 0, and the Q8 remains at 0 as long as Q2 or the Q4 is equal to 0. So in this way the whole process performs the operation of a BCD based ripple counter, in which the values are incremented in form of this kind of a state diagram. Each of the BCD counter that we have discussed so far is represented in a form of this block diagram, and each of this diagram is actually representing a single decade. Say if we are just representing or adding two numbers from 0 to 9, or one representing one number from 0 to 9, that we actually try to represent it in a form of a decade. So it is actually the previous circuit that we have discussed in the last slide is a single decade counter. And if we want to move from say 0 to 9, we would use a single of form of that, or single block diagram of that counter. And if we want to move from 00 to 99, or you can say a 2 decade counter, then we would be requiring two blocks of these BCD counters here. And if we want to represent the whole system in a form of a 3 decade counter, which would be actually having values from 000 to 999, 9, then we would be requiring 3 BCD counters. So each BCD counter is actually a separate decade counter, and if we connect them in a form of this way, that the output of the last one from the first counter is basically becomes the input to the second one, and similarly same for the next one, then they would form a kind of a 3 decade BCD counter. So this is the complete diagram of a BCD counter, and you can see that these connections are actually to the C count input or the clock input of the next counter. So it would be representing 10 raised to power say 0 digit, and it would be representing the tens digit, and it would be representing the hundreds digit. Now we would be discussing the synchronous counters. We have so far discussed the ripple counters. In the ripple counters, we have seen that the flip-flops are triggered by the outputs of the other flip-flops. The triggering source for all the flip-flops is different. Some are triggered by the main clock, while some are triggered by the other outputs of the flip-flops. While in the synchronous counters, all the flip-flops would be sharing the common clock pulse. Generally, all operations are performed simultaneously. Now we would be discussing the binary counters, or you can say binary synchronous counters. First, we are representing a 4-bit binary counter, because you can see that from the diagram, all the clock inputs are connected to the main clock, and they are represented by the positive clock edge of the cycle, because they are connected with the same clock. That's why they are called the synchronous. This whole circuit is consisted of the JK flip-flops, and the output are represented from the A0 to the A3 term, because this is a 4-bit binary counter, so it would start from value 0 and keep on incrementing from 1, 2, 3, 4 up till 15. So in this way, this binary counter works. The flip-flop in the first position is complemented when the pulse that is attached to it, or the clock signal, has a positive clock edge cycle. So with every positive edge of the clock, this would keep on changing or complementing its value. While the flip-flops in any other position is complemented when all the bits that are in the lower significant position have a value equal to 1. It means that for the A1, it would be complementing if all the lower bits, say A0 has value of 1, and for the A2, if both A1 and the A0 would have a value equal to 1, only then it would be complemented. And for the A3, if all the 3 bits A0, A1 and A2 have a value equal to 1, then this would be complementing. So in this way, this binary counter is designed. This is a kind of a more similar way in which we design the counters, because we have studied the basic counter design in the sequential circuits design part using the finite state machines. So this is very much similar to that. And then we also have a count enable pin here, which is actually controlling or enabling the whole of the counter. Say if the value of this enable input is equal to 0, then all the J and K's inputs are equal to 0, and the clock signal does not change the current state of the counter. So all the values would retain A0, A1, A2 and A3 would retain their values. We could do some slight modification in the same circuit to also make it work as the down counter too. And then we could integrate both of them in a single counter in a way that these perform both up and down operation. Basically, we have just added the extra say gates here to represent the downwards operation. So in this way, we have also added the 2 extra signal. Whenever the value of up is equal to 1, then this circuit would be behaving as the up counter, meaning its value will be increasing in this kind of pattern. And whenever we have this signal down equal to 1 and up is equal to 0 at that time, then basically we would be decrementing in a form of this pattern. So if we can combine them, both of them, in a form of a a combined up and down binary counter which could perform both kind of the operation. Here we have used the T flip-flops for the representation here. We could also use the JK for the same purpose too. Now we would see the design of a BCD counter. Previously we have discussed it using the asynchronous module or the ripple BCD counter. Now we will be discussing a BCD counter using the normal or the standard sequential part, in which all the flip-flops are connected to a single clock. Because this is little bit different from the normal binary counter, because it values has to stop at a 9 equivalent decimal value, and after that it should again move back towards the 0. So for designing this, we could follow the pattern that we have discussed in the previous chapter. We would first represent that system in a form of a say a diagram, or in a form of a state table. So if we represent it in a form of state table, we could easily define the inputs of each of the flip-flops that are involved in it. If we say are using the T flip-flop, then we could accurately define what kind of pattern should each of them should follow. And each of them, the input is represented in a form of a single bit, because for the T flip-flop, the normal operation is that if we have a 0 value, then it would retain the current state, and if it has a value of 1 and the input, then it would be complementing that. And because the clock signal is same for each of them, we don't have to worry about the input of one connected to the output or the input of the other one. In this way, we can design a simple sequential circuit that could represent a BCD counter here, and you can clearly see that this could be drawn with the help of 4 T flip-flops, and it would involve on 5 AND gates and 1 OR gate. So in this way, if we just implement this diagram using the 4 T flip-flops, we could represent the function of a BCD counter. And you can see that this structure of the BCD counter is little bit different from the one that we have discussed previously for the ripple BCD counter. There are some other kinds of counters that are also commonly used in different kind of circuit design. One of them is the ring counter. Ring counter is a kind of a shift register in which the output could have a value of 1 bit equal to 1 at a time. It means that for the 4 outputs, only one could have a value of 1 at current time, while the rest would be equal to 0. This could be represented form of a, say, this timing diagram. If you see that these are the main clock pulse, which is connected to all the system involved, and because this is just a shift register, so it is actually representing the whole system here. For the first after the first clock cycle, what would happen is that the T naught would go equal to 1, and after that, for the when the next clock arrives, the T naught would move to 0, while T1 would move to high position or 1. And when T1 goes to 0, the T2 would move to high, and when T2 goes to 0, T3 would move to high. And then again this sequence would keep on oscillating or moving in the same pattern. So in this way, if we consider it as a shift register which has a value equal to initial value equal to 1 0 0 0. So what would happen is that after every clock pulse, the one would keep on shifting right one position, and when it reaches the T3 is equal to 1, then that shifter system will again move back to the reset state, and again the same procedure would occur. So this is just a shift register in which the value of the outputs are 1 at or have a logic level 1 at the one time. So this could be used in different kinds of circuits. Say if we have a count enable pin that is attached to controlling this shift operation, then what would happen is that a 2-bit ring counter would be producing 2 different kinds of input. It would be having one equal to 1 and other equal to 0. Then it would have first one equal to 0 and other equal to 1. Then we could use these outputs to control our decoder. Say then we could combine them in a form of a 2 to 4 decoder, and then for the 2 to 4 decoder we could have a value against each of them at a certain time. It means that T naught could be equal to 1. Then for the next, what would happen is that T1 would be 1, and after that T2 could be 1, and then T3 could be 1, because this would have a 2 bit value here, and from the 2 bit we would have 4 different combination. And we now for the decoder case, for every given combination of the input, only one input remains the high. So we could also design this counter in form of a this way. So this is also very useful in representing different kinds of counter circuits or the related items in the sequential system. Kindly do read these pages for better understanding. Thank you.